Intel Alumni Network's 4004 and MCS-4 50th anniversary. I'm Dave House. I'll be the moderator tonight. It was November 15th, 1971, that Intel ran an ad with the headline announcing a new era in integrated electronics. At the time, that sounded very bold, but it may have been an understatement. But first thing I'd like to do during this webinar is to start with a video from Intel and Pat Gelsinger concerning the significance of this event. Let's roll the video, please.
Hi, Pat Gelsinger here, Intel CEO. I'm so sorry I can't be with you live today, but Intel's mission has me traveling. However, I couldn't miss the opportunity to share in the celebration of this amazing milestone. Happy 50th anniversary to the 4004 microchip. You've made so much possible over the past half century. 50 years. This is a sacred moment for tech. This is what made computing really take off. A 4-bit CPU that clocked at a whopping 740 kilohertz, capable of executing 92,000 instructions per second and accessing 4K bytes of program memory and 640 bytes of RAM. This seems trivial compared to what we have today. A chip with up to 16 cores and 24 threads, 5.2 gigahertz turbo frequency, 30 megabytes of shared Intel Smart Cache, DDR5 memory, and both PCIe 4.0 and 5.0 for the latest storage and high-performance discrete graphics. Moore's Law is clearly alive and very well. Such progress is just a part of our daily reality today. And until the periodic table is exhausted, we will be relentless in our path to innovate in the magic of silicon. Intel is a national treasure and plays a crucial role for our world more than ever before. I recently had the opportunity to chat with one of our founders, Gordon Moore. It was an amazing trip down memory lane. Take a look at what he had to say about this historic milestone.
First, Gordon, I want to tell you how excited I am to be able to chat with you today. In November, we have the 50th anniversary of the 4004, the first general purpose microprocessor. And maybe you can describe the opportunity that you and Bob Noyce saw for the 4004 when we first created it.
One of the things that was being considered those days was calculators. Everybody wanted an electronic calculator. So we got introduced to a Japanese calculator company. This was the tail end. We were Johnny comes lately to the semiconductor business. And they were in a similar position in calculators. But anyhow, we decided this was a good opportunity. And we took a look at what they had done. And they had done the logic design for several different kinds of calculators. These were multifunctional things. And they wanted something like 13 complex circuits. And one of our engineers, Ted Hoff, came from the systems end of things. And after we were lamenting the fact we weren't big enough to tackle 2 chips, let alone 13, he said, I think I could do all these functions with a general purpose computer architecture, and it shouldn't be much more complex than the memory chips you're making now. We were making 1024-bit MOS devices, 6 transistors per bit, so about 6,000 transistors on a chip. Now, this was attractive to me because it gave us something we could make in the large volume, and it was broadly applicable. All of these 13 chips could be replaced by a central processor and a couple of memories, which were standard products. So this looked like another branch beyond semiconductor memory, where we could take advantage of the developing technology's capability.
It is not lost on me that such an accomplishment is the result of dedication, teamwork, calculated risk-taking, and a complete commitment to the task, with no step in the process overlooked or undervalued. Today, semiconductors are the underlying technology empowering developers and powering our customers' innovations. Thank you to all of you for being part of Intel's journey. So let me turn things back over to you for a conversation about how this device came about with none other than the 4004's very own creators, Federico Faggin, Hal Feeney, and Ted Hoff.
Well, that's a lot of enthusiasm, Pat. And thanks, Gordon, for your comments coming all the way from Hawaii. Of course, Gordon was at Intel when the 4004 was developed, but Pat was probably still in school at that time. Maybe that's why he mispronounced Federico's last name. It's Faggin, not Faggin. Well, I wasn't at Intel either when the development of the 4004 happened. I joined in February of 1974, just before the 8080 was introduced. But I worked with all the players during the next few generations of microprocessors. Now, like any good project, there were a number of people who were associated in one way or another with the 4004. Ted Hoff, with the help of Stan Mazer, led the original definition efforts. Federico Faggin single-handedly designed the 4001, the 4002, the 4003, and very importantly, the 4004, with some help from Masatoshi Shima from Busicom. Shima was involved with basically every aspect of the program from the very beginning on the Busicom side, and assisted during the actual chip design. Of course, Bob Noyce helped shepherd the program, and Ed Gelbach saw the potential and drove the marketing and the sales of the of the 4004 and the MCS-4 as general purpose logic replacement. But Hoff, Mazer, and Faggin are generally recognized as the key players and have been awarded for that, recognized for that. We have three members from the team with us today: Ted Hoff, Federico Faggin, and Hal Feeney. Now, Hal had limited involvement with the MCS-4 until he moved into marketing after the announcement. But I'd like to start with Ted, because he was there at the beginning. Of course, Ted, Intel, well, I guess Federico was at Fairchild when Bob and Gordon announced they were going to be leaving, but Intel was officially formed on July 1st of 1968. And Ted, when did you join?
I joined in September. That was really the first day that Intel had a place to really meet other than one of the founders' homes.
Yeah, that's great. And what were you doing before Intel hired you?
I was at Stanford University. I had gotten my PhD in 1962 and stayed on as a postdoc. And my thesis was in the area of neural networks, working with Professor Bernard Woodrow. And I stayed on working under government contracts with Professor Woodrow. And we were dealing mostly in military applications of neural nets, like sonar for submarines and target recognition for space applications.
So was it Bob Noyce that hired you?
Bob, it's my understanding that based on Gordon's observation, which was a few years before Intel was founded, known as Moore's Law, that if integrated circuits continued to get more complicated, eventually we'll be putting systems on chips. So he approached a professor at Stanford and asked if he had any ideas of maybe some people at Stanford that might have a systems background that would be appropriate for a new company. And I was one of the names that Professor Angel gave him.
That's an interesting story. So you were there and worked for a little while before Busicom first contacted Intel? And can you tell us a little bit about your first encounter with Busicom?
Well, let me give a little background. Intel was started to do semiconductor memory. And I have a gadget here. This is what computer memory looked like before the days of Intel. This is what's called a core plane. It's an arrangement of wires, and at each intersection, there's a little tiny donut made out of a special magnetic material. And Intel was founded to replace those little magnetic cores with semiconductors. The problem they felt was computer companies, the ultimate customer, were pretty conservative, and it might take a while before a real market developed. And they didn't have an awful lot of money. There was something like $3 million in initial financing. So what does a company do to sort of generate some revenue? Take on some special jobs. And our first contact was with the company that sold calculators under the name Busicom. And we had a meeting in April of 1969, in which Intel basically agreed, yes, they would make integrated circuits for calculators to go in, Busicom, under the Busicom name. At that point, we didn't know how complex the chips they were seeking. And it was actually about June of 1969 when 3 engineers from Japan arrived at Intel, bringing the full proposed specs for the calculator chips. And I was assigned to be liaison. And being curious, wanting to know more about it, the more I knew, the better I'd be able to help the engineers from Japan meet the appropriate people at Intel. The more concerned I got, and I took my concerns primarily to Bob Noyce. I said, it looks to me like this is going to be a difficult job for Intel. And he basically said, if you've got any ideas of how to simplify it, why don't you look at them? And that's how the project got started.
So I understand there were a number of meetings with Busicom. The first one you had mentioned was in April of '69, and then a second visit where 3 engineers showed up. Do you have a recollection of what that meeting was about?
Well, the 3 engineers came in June to bring the specifications for their chipset. And it ended up with something in the order of 12 or 13 chips, as Gordon mentioned, because there were special chips for each function in the calculator, like to read a keyboard, a special chip to maintain a display made with light emitting diodes, a special chip to operate a printer. And then they were planning to use shift register memory. So there were shift registers, and they were custom for the calculator set. And then there were controllers and arithmetic units and so on. So it began to add up, and each of these chips was fairly complex.
So you got a little bit of help shortly after that, because one of the key players, Stan Mazer, came to Intel.
Actually, a lot of the work I did before Stan joined. In other words, as I said, the engineers arrived in June, and by the time Stan joined at the beginning of September in 1969, but by that time, the fact that while at Stanford, I had worked with both IBM 1620 and IBM 1130 computers and had a pretty good idea of how to make a simple computer. Neither of those machines were terribly sophisticated inside. And so most of the spec was ready. Stan helped me put the last finishing touches on it. And by September 16th of 1969, our marketing director sent a letter to Japan with the specifications that we were proposing and told them they should look at this as well as what their engineers were proposing, to look at our approach as an alternate.
Then the next month, in October of '69, I understand they came over and there were some very important meetings. Tell us about that.
Yes, and basically the engineers from Japan were told, and started working on simplifying their approach. And Stan and I were working on our approach and trying to get it, more details worked out. And at that meeting, where the management from Japan came to California, the engineers from Japan presented their approach, and Stan and I presented our approach. And after that, I was quite surprised to hear the management of the Japanese company say, "We like the Intel approach."
Yeah, that's interesting. So then you continued to work with Stan to finish your part of the definition from an architecture standpoint. When was that completed?
That was complete before the end of the year. There was perhaps one change. The original spec called for the CPU, a read-only memory, a read-write memory, and there was a master timing chip. And it was actually Stan helped work out the details where we integrated the timing chip into the central processor. And so we figured, but at the same time, we realized we need better input-output capability. So we defined another chip, which became the 4003, which was meant to expand I/O capability. It was a shift register. And a couple of things really helped in the architecture. One was that Intel was working on dynamic RAM. So rather than use the shift registers being proposed by the Japanese team, which would be 6 transistors per bit and relatively slow to get at the data, the dynamic RAM was fast and used only 3 transistors per bit. So that looked attractive, but that also meant that the instructions could be executed at a much higher rate. So in effect, we could go to a simpler calculator concept and use cruder instructions, which means a simpler central processor.
So what are some of the challenges that you faced during that definition time? What were the tough nuts you had to crack?
Well, one of the things was learning as much as I could about all those other chips in the family so that I could make sure that the instruction set I was proposing would be capable of implementing the functions of like keyboard scanning, of maintaining a display, of operating a printer, of being able to do floating point arithmetic and the like. So that was one aspect. One of the things, my experience with the IBM 1620, it used what's called binary coded decimal arithmetic. And that's what was to be used in the calculator. But it occurred to me that if you have 2 binary coded decimal digits and a carry, and you add it all together, you end up with a valid binary result, but it's not a valid binary coded decimal result. You add a digit between 0 and 9 to another digit between 0 and 9 and a carry worth 1, you get a number between 0 and 19. And it looked like, suppose we built a binary computer, 4 bits, and had a special instruction that would take that number between 0 and 19 and convert it to a valid BCD digit. And that looked like a pretty simple instruction to implement. So that was one of the hurdles, you might say, to get over to make the machine, simpler and easier to build. One
of the things that was quite interesting is that it was designed, you did the architecture to fit inside a 16-pin dual inline package, which must have been a constraint. Why was that choice made?
Well, actually, at the time we were defining this, Intel was still developing its version of the silicon gate process. And I believe it was Gordon had come up with a technique that helped improve the ability to put down the aluminum layer over a layer of oxide. And it was called phosphorus doping or phosphorus glass. And the problem was that if you put that chip in a package that made of plastic, moisture could work its way through the plastic to the chip, and it would react with that phosphorus glass and make phosphoric acid, which is a wonderful etchant for aluminum. So the idea is, the feeling was, we will not be able to put Intel Silicon Gate chips into plastic packages. We'll have to use more expensive ceramic packages. And of those, the cheapest was the 16 lead package. So one of the reasons for going with 16 leads was to save on the cost of packaging. Now, ultimately, they worked that out, but the 16 lead limitation we kept with, because it turned out with a 4-bit processor and a 4-bit wide bus, you didn't need an awful lot of leads to couple the chips together.
Yeah, I see. Was there anything else about that initial time in 1969 that you wanted to talk about?
Well, I don't know if we want to talk at all about the 8-bit processors, but there was an overlap toward the end of 1969 with a company from Texas, which came to us with a request for a memory chip for a processor they were building. And Stan and I looked at it and came to the conclusion their processor wasn't that much more complex than the 4004. We didn't know it under that name at the time, but the processor for the calculator set. And so we counter-proposed that they do that as a single chip. That led to our first 8-bit processor, the 8008. But that didn't come along until well after the 4004.
You got started with that.
4004 was the first one done.
Okay, well, I think now we can go to Federico, who played the central role in all the development. Federico, you're Italian.
Yes, I'm Italian.
How did you get to the United States?
By plane.
Give us more detail.
Yeah, I was born in Vicenza, which is near Venice, and I grew up there. I went to a technical high school. And when I was 18, I ended up working for Olivetti, and I was interested myself on computers on my own. I did not study those at school, and lo and behold, I started working on the design and building of a small computer. It was an experimental computer, and I ended up for a series of circumstances to actually design all the control of the machines and most of the rest of it, so about 60% of the machine, and building it with 4 technicians that worked for me. So by the end of 61, I had a computer working with 4K by 12 core memory. And I decided that, well, I better go to university at this point. I think I wanted to understand transistors, and integrated circuits were in the horizon, but they were not out yet. And so I studied physics. And by 65, I came out with a degree in physics.
And then you went to work for, was it Olivetti then, or?
No, the Olivetti was where I designed that and built that small computer. No, I went to work for SGS Fairchild, which was the company that had the rights to manufacturing rights and selling rights for the Fairchild integrated circuits, bipolar integrated circuits for Europe. So that company was near Milan, in Agrate Brianza, and I developed their first MOS process technology in the second half of 1967. And I also designed the first 2 commercial integrated circuits of SGS Fairchild. Then they decided to send me for 6 months in the US. That looked like it wasn't a good decision because I'm still here.
You never went back to work. So was it at Fairchild in California that you developed the silicon gate technology?
So I joined Fairchild in 1968. It was February 1968, working for Les Vadez. It was, but I was working for SGS, but SVADES was my US boss. I was, my Italian boss, was obviously in Italy. And when I joined, I had a choice to design a shift register. Those days, shift register were the only read-write memory that was possible with integrated circuits. Or the other choice was to develop a silicon gate technology, because there had been some experiments done at Bell Labs where they showed that you could actually make MOS devices with silicon gate, and that's all they told me. They didn't even tell me that there were already experiments done at Bell Labs. But I was put in charge of that project because I already had developed an MOS technology where I came from, and I quickly figured out the key thing that needed to be done. Basically, nobody understood how to actually do silicon gate, the architecture to do silicon gate. Then I had to develop the etching, of the silicon. In those days, the silicon was amorphous. Eventually, I found out that it would break at the oxide step. So I found a way to use polycrystalline silicon in order to have step coverage, and basically by June, actually by April, I had working transistors and the process was working. And then I designed a integrated circuit, the Fairchild 3708, which became commercial at the end of 1968. And that was the first integrated circuits to use silicon gate. That was 5 times faster than the metal gate version. And of course, the leakage current was between 100 and 1,000 times less, so that one could do dynamic circuits very effectively with MOS devices with very low frequency, and 5 times higher frequency, but also much lower frequency, which was important for dynamic memory. Without the silicon gate, it would not have been possible to make dynamic memories with MOS devices.
So what was the function of that device, that integrated circuit? What did it do?
It was an 8-bit analog multiplexer with decoding logic. It had very big transistors. They had less than 100 ohm on resistance, which require very powerful transistors. And it had a decoder so that you could decode 1 of 8. And those transistors had to be much faster than they could build with metal gate, not only, but also the leakage had to be, as I said, much lower than it was. And so the 3708 replaced the 3705 by the end of '68. And that was using wafers, by the way, they were made in the fab that was in the R&D lab. However, there was a problem because silicon gate could not allow you to make bootstrap loads because you couldn't make isolated capacitors, and that was a major problem for which Fairchild was not interested in taking on the silicon gate technology and using it for their random logic design because they couldn't do the bootstrap load. So the bootstrap load was a real. I couldn't sleep. I mean, to find out a solution to that because I really thought that silicon gate was the technology that was going to change the world of LSI. In those days, LSI was 1,000 gates, where in the 2 or 3 years in the future was expected to be able to do that over 1,000 gates. And I felt that the silicon gate was the technology for LSI, not the metal gate.
So then you joined Intel. When did you join Intel?
I joined Intel in April of 1970, few months after I finally cracked the nut of figuring out how to make the bootstrap load. At that point, I felt that nobody could stop me because with the bootstrap load and the other invention of mine, which was the Berry contact that would allow 2 layers of interconnection. Now I could make integrated circuits that nobody else could do. And so that was the fundamental technology to, that would allow to do all the pieces of a computer.
So how did you get to Intel? You'd worked for Vadez at Fairchild. Now Vadez is at Intel. What happened?
Well, in the beginning of 1970, I was a little disappointed with Fairchild because they were not accepting the silicon gate technology. The only company that had silicon gate was Intel, which of course they took what they understood that was a major technology. And so they had developed already a memory, the 1101 memory that was announced in October of, if I remember correctly, of 1969. And so Intel was the only company that they could do complex circuits. I had a job offer from National Semiconductor early in 1970. They wanted me to copy essentially the process. I said, no, I'm not going to copy anything. So I didn't join them. And I called Vadez and I say, Vadez, do you have a complicated circuit for me to do? Because I think I'm ready to tackle big integrated circuits. And he said, yeah, I think I got something for you.
So this is April of 1970, and Hoff just said that the design, the definition, the architecture documents were written at the end of 69. What happened during those 4 months?
Well, I'll tell you what happened, that nothing was done in between. And I think it was a couple of days after I joined Intel, Stan Meso said, let's go to the airport to pick up Shima. Shima is coming to check on the work. And so I said, oh, great, let's go. Yeah, I'd like to meet Shima. Shima was the engineer that eventually did the firmware for the calculator, and also was involved very much with the design of their version of a programmable solution for calculators. So I went to the airport, and he was eager to check. I'm here to check. I think he repeated, I'm here to check probably 10 times on the way to Intel. And he didn't even go to the hotel to sleep. And he said, where is the logic circuit of the CPU? Because in those days we had not named the parts yet. So I said, what do you mean logic? There is no logic design of the CPU. But you said that it was ready. I said, I didn't say anything. I just got hired. I mean, I just know they just gave me the spec of the 4 chips. I don't know anything. And I gave it all the stuff that Stan Meso gave me, all the documents, and I gave it to him. That's what I have. I have. And basically, he was so mad at me, and I couldn't, it took me a week for him to realize that I could not have done what had been promised to him. But of course, now I knew that I was 6 months late.
Well, I understand that Intel was very short on chip designers, and they were all corralled into making memories at that point in time. And of course, Hoff and Maser were not chip designers, and so you arrived and kind of got all delivered in your lap with, as you said, it's already 6 months late. So tell us about how you went about designing.
Well, I mean, obviously, the first thing to do was to understand what I was supposed to do, right? So that took me about a week. With Shima help, it took me a little less because he understood exactly what he wanted. So it was very helpful to have the customer that I could interact directly. And I found a couple of mistakes or missing things in the architecture. So I fixed those. And so now we had, everything seemed to be correct to my understanding, but then we didn't have any methodology for random logic design at Intel. There were no circuit blocks, no logic, no way to do logic simulation. There was very little, in companies in those days like Fairchild that had, they did custom designs. They would have computer simulations and circuit blocks already made, ways to evaluate the layouts and so on. I mean, there was for today's standard, it was a very limited type of computer aided design, but they had a sort of computer aided design, and there was nothing. And so I had to figure out how to quickly, first of all, then before that, I had to have a schedule, right? So the schedule was, but Des had created a schedule that was, I was supposed to have everything done by the end of December. How can you do a microprocessor that nobody has ever done before in 6 months or 7 months? I mean, that's of course, when the schedule was done, it was done 5 months earlier, but still, it was very hard. But anyway, to me, I wanted that project. So I said, okay, I mean, I'll do anything I can because I want to do it. I was waiting for doing something of that nature. I knew that sooner or later a CPU on a chip would come out. There were discussions at Fairchild where that was, was understood to be 3-4 years in the future. And I wanted it. I wanted to do it. And so, I said, okay, I'll make a schedule where by December of this year, you will have the 4 chips. And I actually missed only for 3 weeks. And only because the first run that came out, it was the very content was left out of the manufacturing. So I had all the transistors were not working.
So you had to not only design the logic, but you were very much involved in the silicon process, and you didn't have well, Shima came and helped for a while, but you didn't even have experienced chip layout people at the time. You had to train them as well.
Well, but Shima didn't know very much about MOS devices. I mean, Shima was a good logic designer. And Shima was a very, very careful, very attentive and very careful at checking things. And so I used him for what he knew. And in that process, he stayed about 6 months and he really learned a lot. And it was a big help to me because I was alone to do 4 chips. And the other thing is that when I told Vades, but I need a bootstrap load here to make this stuff. Don't you know that the bootstrap load cannot be done with the silicon gate? Yeah, of course I know, but I have invented it. I actually even tried it, and it works at Fairchild just before coming here. And he said, I don't believe you. So he got me in touch with he wanted me to explain to Froman, that Froman, who was had joined a few months earlier to design the first floating point floating gate chips. The 1601, 1602, they were basically programmable by using tunneling. You could program memories, ROM memories that then would be non-volatile. And so it was the beginning of the EEPROMs, and then eventually the flash memories that we have today. So that was a major big new development also that started at Intel, again made possible by Silicon Gate, because Silicon Gate could be could be covered by oxide completely, oxide grown at 1200 degrees C, which is quartz. And so it's the best insulator that is possible. And so that was another piece missing that the silicon gate technology made possible. So I will get to the Drossman, but you understand that there was a lot of work to do to design the worst case design for the logic. I decided to design by using, essentially, instead of using computer simulation, to use graphic design, the stuff that I had learned at my technical high school to design vacuum tube circuits. So using those techniques, I could do quick calculations. Also, I decided to go from specification to circuit design, and where the circuit design, one document where the circuit design already had the understanding of the layout, so that I could evaluate the capacitances of the layout. And so by doing it this way, I would eliminate, first of all, errors. That there are all these errors in translation. So in this way, I eliminated all the possible errors in translation, and I could do a simulation with those simple tools that I had developed for myself. And that way, I was able to, I had finally a methodology that I could use to do the design and start the layout. Now that I could start the layout, however, there was no layout draftsman. So the first draftsman that I got was a Rod Sayer. He came from Lockheed. He had only done mechanical design. He didn't even know what a chip was or transistor was. So basically, I had to also draw everything given to him in rough form, and then he would put it in good form in the composite drawing. But of course, that was good for me because I learned to do complicated layout, because the ROM chip, that was the first one, the 4001, that chip also had a fair amount of logic inside. And so I decided to do the 4001 first, the 4003, the 4002 next, and then the 3, and then the 4. So I would have developed, by the time I got to the 4004, pretty much all the building blocks would have been developed. Because these other chips were full of logic as well. They were not just conventional memories. They had to decode instructions, the IO instructions. They had to have on-chip refresh for the RAM, and so on and so forth. So it was only after the 4001 that I was able to get one more draftsman, and this one was a draftsman that came from Fairchild, and it was the one that actually did the 3708 layout for me back in '68. Julie Hendricks, and she was able to, so she understood. Since then she always did bipolar, but she understood layout, and so that was relatively easy for her to come on board, understand how to do random logic with MOS. And then by the time we got to the 4004, I had access to Barbara Manis, and she was able, she joined the other two, because that chip required three draftsmen simultaneously. Otherwise, it would have taken too long. In those days, we could design about 12 to 15 transistors of random logic per day. Per draftsman. So with that kind of productivity, you can easily compute how long it's going to take you.
So there's 4 chips. You designed all 4 of them. Which one did you do first?
The 4001. The 4001 came out in October. It came out just before Shima went back to Japan. So Shima actually got to see that chip worked first time. It was everything worked, in voltage margins, temperature, speed. Everything was, it took me about a week to go through a mini characterization of all the things that I was concerned about. So that told me that my methodology was working. And that was so, my heart started started working better after that because if the 4005 had not worked, I mean, the mess would have been huge.
So then you did the 2 and the 3 before you started on the 4, huh?
That's right. And then the 4, the layout of the 4, but they were all worked in parallel. I couldn't, they could not be put in series. How can you do it? I mean, a chip to go from design to first silicon. The minimum that you can do is probably 5 months, in those days, so 6 months. And so I mean, it was one after another, but all in parallel. And in those days we use Rubylith. Can you imagine? After you do the composite, you have to cut and peel every layer of masks, and in a cutting table. I mean, it's crazy stuff for today's standard.
It's amazing how much difference there was then and now, and even in between. I know when I was there and we were doing the 386 and the 486 with Pat Gelsinger, we had a whole silicon technology department with hundreds and hundreds of people developing silicon processes, and we had literally hundreds of people on the design team doing all different parts of the chip and the design tools and all that sort of thing. And this was all wrapped up with one person, with you, with the 4004.
And 6 months of Shima and the Draftsman. That's it. And one technician, because and then Hal Feeney helped me with the tester, with developing a characterization tester, because that was also fundamental. There was no tester for and no tool to do to figure out if we had bugs. How do you know? How are you going to figure them out, and so on? So Hal and I did the tester, starting with a discarded memory pattern generator, and with that, by October we had a tester, so that the first chip was we could test it and keep on going. So then in November we got both the 4003 and the 4002 came out, and 4003 worked right away. It was a simple chip, and the 4002 also worked perfectly. There was only one little problem that had to go through and respin. And then December was at the end of December, exactly as I said on my schedule, came out the first wafers of 4004. And don't tell me I was pretty ragged that night when I got the first wafers.
I imagine you had a lot of free time on your hands during those 8 or what was it, 9 months or so this was happening. You must have been working unbelievable hours.
Well, 70 to 80 hours a week, not that much, right? My wife, I had a big, my first born was born in March of 1970. So I came on board with a month-old girl, Marcian, with she's 51 now, and so I was glad that my wife had her sister helping, and then I told my wife that to go back with her sister so that I didn't feel guilty every night coming home, giving her no support. So she left, I think in probably June, and then she came back in September. So I had a good run.
No distractions during that time. So you had fully functional chips, all 4 of them, when?
Fully functional in March. So the first run, as I mentioned earlier, was there was a mistake, and that was so it had to be redone. The mistake in manufacturing, and so it was in middle to second half of January. I don't remember the date exactly, that I got the first run where everything was done properly. And so that night, I spent probing, and everything that I probed worked, and I was, I was elated. I mean, to have now everything working was fantastic. And so at 4 a.m. I left the lab and I went home. My wife was waiting for me, and she asked me, "How did it go?" And I said, "It works." I mean, that was one of the most fantastic times, to know that finally you have done something that is going to change the way we do stuff. And it was very clear to me that was a watershed moment. Then in the next week, we found a couple of minor mistakes that were fixed. And so everything was done in March, including 4 ROM codes that by that time Visicom has sent so that we could give the ROM code for the calculator. So by mid-March, we send all the ROM codes, the new 4004 that was fully perfectly working. That's the one that went in production. And they already had the 4002 and 4003s. And then I got a call a week later. Shima said he just plugged them in, and it typed on the calculator a number, and then another, and the multiplication worked.
So that's like March of 1970 that you're delivering functional chips to Visicom.
71.
71. But the announcement didn't happen until November. So what happened between March and November?
Well, between March and November, I found out that, well, actually I had found out before that Visicom had exclusive rights to the 4004, and I didn't like that at all. I just, I felt that, that those chips, despite being designed for calculators, they could do very well for control applications. And so, but I basically got some pushback, both Ted and also Stan were telling me now that the 4004 is not really good for, it's only good for calculators. And but the 8008, of course, yeah, that certainly it would be nice if we could sell it for everybody. And I said, well, I mean, I don't agree with that. I think it's going to be good for control applications. So the first opportunity I had to show that you could use it for control application was when I had to design a tester, a wafer tester for the 4004. And so in that tester, I used 2 chips, one 4004 to create the patterns that to compare, and one 4004 to do the control for this tester, so that you would control the entire electronic of the tester. And so I program, of course, in machine language. There was no assembler, there was nothing, and I used the 1702 that were just available, the electrical programmable and UV erasable EEPROM that Intel had developed, which, by the way, did a great job later on for the company. And so in this way, I was able to prove myself how a designer could design the chips for a system that they wanted to do, and also convince myself that was a viable way to do it, because it saved me about a month if I had to do a one-off design. And so, and then, having done some software, then that software typically can be reused. So you make an investment, but that investment can be reused and so on. So on that strength, I started, in my style, just bugging people to, bugging our management to, to get out of from the exclusivity agreement. One day I got a call from Shima, and he told me that things were not going very well. I said, why? Well, we cannot compete, and we have to pay too much for the chips from Intel. I said, well, I say, so anyway, so the company was not doing very well. So I felt that was an opportunity to, and I told Bob Noyce, I went to Bob Noyce and said, Bob, this is a good chance to get out from the exclusivity, because they, if you lower the price, I'm sure that you can get out of the exclusivity. Anyway, it turns out that they were able to do so, and then I think it was by August or so that the decision was made that Intel was going to announce the 4004. At that time, we were already designing the 8008, so there was another big horse to ride later on, and certainly Ed Galbach, who was came from TI and understood much more than the prior VP of marketing, understood much more the random logic sort of marketplace, was very, very instrumental to making that decision, because in talking to him, I realized it was the one that was more favorable of all three of the top manager. Andy Grove considered microprocessor a nuisance, something that was absolutely uncalled for. The company should really, focus only on memories, and so this was not something that he was willing to support.
But I guess Bob Noyce and Ed Gelbach were two big supporters and two big advocates for the microprocessor and those early days. And Ed, coming out of TI, where the TTL business was, they were king at TTL at that point in time with their 7400 series. He certainly understood logic, and even
but TI, Dave, TI was it was one of the top producer of random logic MOS integrated circuits. I mean, custom integrated circuits. I mean, it was a big chunk of their business. So not just TTL. I mean, also MOS.
Mm-hmm. Yeah. So Ed was an advocate. Bob Noyce were an advocate, and the announcement hit, I guess, what was electronic news on November 15th, 1971, which is 20 years and about 3 weeks, announcing a new era in integrated electronics, where they basically said, all this random logic that you guys been doing, you don't need to do that anymore. Now you're going to be able to program these microprocessors, and that was the big coming out date and the big anniversary that we're celebrating. Of course, that was followed. You went on and managed the development of the 8008, and Hal Feeney worked for you in that time.
Yeah, I was supervising the project, and Hal did all the detailed work. By that time, of course, we had all the pieces, so it was more of a routine job as opposed to being an emergency.
So interestingly, the 8008 was announced about 4 months after the 4004, because it didn't have this exclusivity issue to work out. It was March 13, 1972 that the 8008 was announced, and then it was April 15th of 74, which was a little more than a month after I joined, I think, that the 8008 was launched and really got us into that business. And you played a role in all those products.
Yeah, especially the 8080, which took me 9 months to convince my management to let me use 40-pin packages. Okay?
You hired
if we had 40-pin packages for the 4004, I could have designed a 4 microsecond instruction cycle.
I understand one of the issues with the 4000. I understand understand one of the problems with the 4004 was the width of the package, because the 16-pin package is what, 3/10 or something like that of an inch.
Yeah, but you know, but if a 40 pin, a 40, well, yeah, I mean that require a very small chip. If you know if we had to do, if we didn't have a bootstrap load, we could not have done it. So or we could have done it by using static logic. Static logic would have been way, you know, twice the size, but then twice the power, and also, you know, and also half the speed. So I mean, it was, you know, 16 pin would have been the wrong idea. It couldn't fit in the package to start with. So it's just not possible. I mean, you know, basically the MCS-4 without the bootstrap load in those early years, it could not have been done. It would have been a paper tiger. That's it. It's as simple as that.
So you brought Shima, you hired Shima into Intel to help you with the 8080, as I recall.
Yeah, and Shima, you know, because I appreciated his, you know, thoroughness and his, you know, and by that time he had figured out, you know, he had learned a lot. So after working together with him, you know, for the first 2 or 3 months, you know, teaching him the rest of the stuff that he didn't know, you know, then it went on its own. I mean, it really, you know, it required, of course, you know, regular supervision, but it, you know, the 8080 was designed by Shima from a specification architecture, which I mostly was responsible for. Mazur had a little, you know, helped with a couple of instructions, but fundamentally the new architecture was my work, and my most important, you know, my risk taking with management, because I was bugging them to letting me do it, and so. And finally, I got the permission to do it after, you know, after 9 months, as I said.
Okay, well, before I go to Hal, I want to plug your book. Federico has written a book by the name of Silicon, and from the invention of the microprocessor to the new science of consciousness, which he gets into the second part of the book. But in there, he's got the first ad from Intel about announcing a new era of integrated electronics. So how can they get a copy of this book?
Oh, yeah, Amazon, just, you know, Faggin, and there is only one book.
That's okay. Well, and there's some very interesting stuff and a totally different topic about your work with consciousness in the recent years that go on in the end. But let me now go to Hal Feeney and talk to him a little. And we'll get back together. Hello, Hal.
David.
So when did you join Intel?
Yeah, well, I joined Intel just a short time before Federico did. Joined Intel on March 9th of 1970. But as things turned out, I joined on March 9th, but I was already scheduled to get married at the beginning of April. So I took off, got married. Wife and I took a short vacation and came back, and that's when I met Federico. He was sitting at my desk at the time when I got back, and this is one of these times where Intel was a little bit lean on office furniture and those types of things. So for about, I don't know, 3 or 4 days at least, we shared one of these old Defense Department type desks with pull-out trays on a metal desk, and we shared that. But in terms of getting involved with the 4000 series, I was somewhat on the periphery of it. By periphery, I mean being the office right next to Federico's. So I got to hear comments, screaming, comments from Shima from time to time on the progress of things. But it was very, very interesting.
What were you doing before Intel? How did you get there?
Oh, before Intel, I'd worked for a couple of summers when I was in school at Hughes Aircraft. And then I joined General Instrument Corporation, had a design lab in Los Angeles. And I joined one of the people I worked with at Hughes and was at that design lab for a couple of years. But it turns out in 1970, there was a downturn in the semiconductor market. And GI at the time was the leader in MOS metal gate technology. And as a result, they felt the impact of the downturn in the market before anybody else did. So GI closed up their design office, and options were to move someplace else. I started looking around, and I was lucky enough through a friend of a friend to make contact with Intel and ultimately Les Videz.
Were you hired to do the 8008?
Yes, I was hired to do the 8008, and I had to start on that by the time that Federico arrived. And we went through probably 2 or 3 months of work on the 8008. And then things turned south because the 8008 was also designed as a custom chip. And as a result, the customer we were doing it for, Computer Terminal Corporation, started having, I think, both business problems, but concern problems on whether or not they could use it. They were a major shift register customer of Intel's, and Ted could shed a little bit more light on the discussions in late 1969 that he had with DataPoint. But things turned down on that project for about a 4-month period of time until October. And so I bounced around and did a few things, and then I got involved with Federico on the tester for the 4004. And looking at the tester for the 4004, it was a situation where that same tester and the same tester concept could be used on the 8008. All we had to do was just change the pin assignments in it. And coupled with that, by the 16-pin package being a limitation with 4004, and the initial design or concept for the 8008 was also to have a 16-pin package. But we were very fortunate, and again, this is driven through Andy's edict, really, to use small packages. We were at least able to tag along the 1103 memory used a 18-pin package. So using the 18-pin package allowed us to bring out a little bit more information to the outside world and limit the amount of actual hardware or actual random logic that we had put around the outside of the chip.
Well, with a 18-pin package and an 8-bit bus, you don't have any bits left for control, do you?
Well, the 8-bit, in this case, the 8-bit bus was a bidirectional bus. So we did have other pins available. We needed pins for voltage, we needed pins for clocking, and we needed pins to tell us what state the processor was in at any given point in time. But that was going on. Go ahead.
But then at some point you moved into marketing in the marketing organization. When did that transfer happen?
Okay, we moved along and got restarted again with the 8008 in October of 1970. So from that October timeframe, with a little time off to focus on the 4004 in January and December, moved ahead, had sample parts for the 8008 in late summer, and then I got involved in the launch of the 4004 or the 4000 series in November, and at the beginning of 1972 in January, I moved from engineering to marketing. And that's an interesting situation because in the engineering side, you're taking a look very much at a chip and the way it can be used and whatever, either through the eyes of the company buying the chip or your own eyes in terms of designing it. And getting into marketing, suddenly the chip is being looked at by dozens, hundreds, maybe 1,000 different eyeballs, and having different ideas and different concepts of, well, what if we did this, or what if we did that, or how would things change? And that became very important for us. But the big deal with Intel marketing microprocessors was that they got into it as a business proposition, kept bootstrapping their way in through through doing custom chips and bootstrapping their way along. They didn't have users manuals, they didn't have design tools, they didn't have all of the other things that eventually came along to make Intel very, very successful in the eyes of the customers in the marketplace.
Yeah, I remember that, with TTL, you just had a data sheet and that was it. And then with memories, the data sheet got a little more complex, but was pretty straightforward. You throw somebody a 4004, and people have been doing sequential state logic design. All of a sudden, they're in a totally different world because it's largely software programmed. So what kind of materials were generated, and how did that all happen to help with design?
Well, it was kind of a step-by-step process, but at the point where we were getting ready to come to market, Intel was still in that mode of we must have a single page data sheet. There must be a blue data sheet, as in the case of Intel's colors, and all of that was important from a marketing or from a management perspective. But the reality was that we needed to have books that would explain the instruction set, explain how the machine worked. And eventually in those books, we also were able to put some circuit diagrams that gave hints to people of how they could begin designing their systems. And along in that same time, after the 4004 was developed, and then decision was made to bring it to the marketplace, there was work in Ted Hoff's organization and his organization was titled Applications Research, and there was work in his organization to develop some demonstration boards that would show off what a microprocessor could do. And that was at the same time that Federico was lobbying to move further ahead and bring the 4000 series into the market. So there was the problem that none of these tools that we need and love and have today existed at that time, and they literally did have to be bootstrapped along. And remember Ed Gelbach telling a story when we did the oral history of the 4004 for the Computer Museum, that his biggest challenge was convincing Gordon that we wouldn't be competing with our customers. And kind of going along with that same idea, remember one time he came to me and said, I looked at the customers for the all of our memory chips and all the we're dealing with every major computer company and doing exceptionally well with them. And then I look at many of the customers for the microprocessor, and it kind of reads like, instead of who's who, it reads like who's that. And part of that really meant that the customers that could adapt very, very quickly to using the microprocessor were small, very agile companies, and they moved quickly. And the computer companies instead moved at a much slower rate. And we've seen how the center of computing has really moved from being the big companies that were leaders back in the 1970s to many other companies that are now very large companies, but grew into the microprocessor from the point of view of being very small companies and changing the idea of how the market really worked. Also, going back at that time, Federico made the comment about the time that it took for us to go from a decision to market the microprocessors to the point of when we brought them out. Intel had a standard, not necessarily a logo, but a standard tagline at that time of Intel delivers. And that came about because of the situation with other competitors, where they were often products were virtually announced, but often did not make it into the marketplace. And Intel always had the goal at that point in time of having product on the shelf. So a customer, we announce a product on November 15th, the customer can call in and say, I want to buy one right now. But again, with that November 15th announcement of the 4004, the other piece that had to go along with it. And as Federico pointed out, Busicom was having some problems. Busicom, we negotiated the price with them. We had a release from Busicom to make the products available on a broad basis, but with one caveat. Customers could not use the MCS-4 products to compete with Busicom. So every customer that either bought a sample or got a data book from Intel also had to sign a release that said that they were not going to use it in a calculator format.
So who wrote these manuals and did all this work? And how big were the books? I remember Intel distributing these blue books about the 4004 and 8008. Who wrote those and how many pages were they?
For the 4004, Federico and I got involved in developing those, writing them and shaking them out. And they were probably, I'm not even sure about the size of them, but probably in the ballpark of 40 or 50 pages of manuals for the 4004. Then we got to the 8008 and it expanded a bit because by that time we had a little bit more product information available. But probably the most important thing that happened during that time, I can look back on it historically and say, you know, Intel was very, very lucky in terms of getting into the microprocessor business, because instead of having custom chips that were really locked to Busicom, really locked to CTC or Data Point, those chips were also general purpose computer chips that could be used for a variety of other activities. And as a result of that, Intel was able to sell them to other customers. Intel kind of made its own luck with the work that Ted did back in late 1969, such that the products were general purpose, were programmable for Busicom. And reading some comments that Shima made about Busicom and about the life of the microprocessor there, they did a Busicom calculator that was shown in the tape. But also, in addition to that, Shima made some comments about moving ahead, doing ATM machines and point of sale machines and that type of thing. So there was flexibility built in for what Busicom was doing.
Can you tell us some of the early applications of Intel customers other than Busicom?
Yeah, some of the earlier applications were, I mean, almost anything you could think of, but the ones that were in volume production were companies like NCR doing perhaps a dozen different cash register at that time, moving really to the point of sale model, dozens of different types of machines with many, maybe 3, 4, 5 ROMs, 4001s in each chipset. So we were managing, and that led us into a different thing with Intel too. Instead of managing just shipping chips, we managed and set up a program to ship full chip sets, because it made no good to get the 4001s and not get the 4004s or vice versa. So in doing that, we had NCR, there was Toledo Scale was another one that had similar devices. There were some designs that went on, I think, looking at doing petroleum dispensers with gas stations and literally almost everything you can think of. The 4000 series became, you know, Intel's entree to microcontrollers. And then 4 months later, with the announcement of the 8008, that became Intel's entree into what we see today in terms of a processor or multiple processors on everybody's desk.
I recall names like Toledo Scale. There's a traffic light controller. There was a blood analyzer, but all of it was basically random logic replacement in the early days.
Yeah, they were all random logic replacement, and they were, you know, unique conceptual ideas. At the time the 4004 was announced, there was also a little book pamphlet that we designed that was called The Advantage. And it's the advantage of, or I'm sorry, the alternative, not the advantage, but the alternative. And it's the alternative to random logic, and a different way for engineers to approach designs and to make things more effective. But in terms from an Intel perspective, again, going back to this idea of Intel being somewhat lucky, but creating its own luck, independent of doing anything with microprocessors. As Federico pointed out, Doug Froman was doing the EEPROMs. And in designing the EEPROMs, there were a unique set of challenges there. Once the EEPROM was designed, it had to be programmed. And Ted's group initially designed a suitcase-like device to program the EEPROMs, but these were expensive, a little bit difficult to work with, and so forth. And as a result, he used the 4004 and similarly used the 8008 to design programming boards for the EEPROMs that could be used by anybody and were substantially less expensive than the suitcase device that was there. And so,
okay, before, go ahead.
I was going to say, suddenly we had this symbiotic relationship that the microprocessors were being used to program the EEPROMs, and then along the way, as special development boards were being designed, then the EEPROMs could be used for developing systems for the microprocessor. So it's kind of a hand-in-hand approach that is very significant.
Yeah, let's bring Ted back on this topic because he was doing a lot of the work. We switch him onto video. So Ted, Intel eventually created the blue box, the MDS system, and it played a huge role in Intel's success in microprocessors. And I remember when I joined, we had more revenue selling development tools than we did microprocessors. But you were involved, a separate organization was set up to do that, and Bill David Allen, Jim Lally, and a bunch of people worked on that. But you did some of the very early work. Hal was just mentioning it. Just comment on the early work you did to help customers design with the product.
Well, we did a number of things. One, if you look at the contract that was signed with Busicom, while it did have that restriction about calculators, it did anticipate the sales to other venues. And as a result, Stan and I produced a number of documents trying to teach people how to do different functions, like analog to digital conversion, and how to replace, other logic circuits. And so we did write up a manual. I believe it was produced. I don't have a copy anymore except on Xerox, but I think Intel still has a copy of that, and the number went out. And then we did these little boards so that you could do a breadboard, and then the marketing group took it over and built a business out of it. And in fact, one of the experiences we had, the first time our responsibility, by the way, was to build that EEPROM burner, as we called it, to put the code into the EEPROM. And the first one we did used wire wrap logic. And the problem was, that was great for the first one, but the second EEPROM that came along had an entirely different programming algorithm. And so it meant a completely new design. We said, well, if we're going to do a new design this time, let's use the 4004, which was available. And we had a gadget that the next time they changed the algorithm, with just a little bit of change in code in a PROM, we were able to program that new EEPROM. And we told outside vendors of EEPROM programmers about our experience, and they became customers for microprocessors.
So we were some of our best examples. I remember another key item that was decision made, maybe it was in 73 or so, was the addition of field application engineers. And that was a new concept, as I understand it, to the semiconductor business. And when Intel started adding field application engineers, one of the big things was for them to show people how they could do random logic using our microprocessors. I think Ed Gelbach was part of that decision.
And another aspect that came out of it, it's sort of like random logic. There was a lot of fear in marketing about the whole idea of competing with your customer computer companies. But it turned out those computer companies themselves had needs for little processors, typically somewhere inside one of those big mainframes. And they ended up becoming customers for microprocessors to perform those little peripheral functions that take place. So that fear was unfounded. And in fact, that was one of the things, not only Federico, but Stan and I also spent a lot of time trying to convince marketing and management that this should become an Intel product.
Well, I'll tell a personal story. I wasn't there when the 4004 and 8008 were developed, but I was designing mini computers at a mini computer company, Computer Control Corporation, and I saw the announcement of the 4004 and the 8008, and I studied the data sheets and the manuals, et cetera. And I went home and I told my wife, I said, I learned two very important things today. And she said, what? And I said, one is my job's going to change industries because computers are going to be designed by semiconductor companies, not by system companies, because I was doing high volume, low end mini computers. She said, what's the other one? I says, well, my job's going to change coasts. Those guys are all on the West Coast and we're in Boston. She thought that was pretty important. So the thing about competing with computer companies was very true, except I know that we had all kinds of controllers for magnetic tape, for these removable disk units that we used in those days, for printers, various early printers, for paper tape readers and paper tape punches. All of them required control logic, and it was originally done with the street. Every time anything changed, you had to redesign it, like you said, Ted. So I experienced it from the other side before I wound up joining. Let's put Federico back here. He's played really the central role. He's the guy that designed the chip and the process and all that sort of thing. We're running at the end of time here. And this has been great. I've enjoyed talking to all of you. I learned a lot in this process, and I bet everybody else did. I want to just remind the audience that Intel Alumni Network has a series of events, and just like you heard about this one, you'll hear about future ones next year, and there will be announcements going out, and you can go to the website and check it out. And so please stay tuned for those events. And I want to thank everybody that joined, but I particularly want to thank our three panelists. We've come to the end of the period. I understand from the chat box that there's been a lot of positive things said about the panel. So congratulate to all three of you. So with that, I think we'll wrap it up. And thank you all for the work that you did.